Hello, thanks for tuning in. My name is Mark Claypool. I'm a professor at Worcester Polytechnic Institute. It's a engineering school just outside of Boston, Massachusetts, USA. I did this work with Pinhen Zhao and Ben Peters. They're undergraduates at WPI. And then Jay Chung is a former PhD student of mine. He currently works at Viasat, and he sponsored this research. So the work we're looking at is looking at TCP over a satellite network. I'll talk about that in a bit. And then in particular, we're looking at competing TCP congestion control algorithms. So to set up the problem, you think about satellite networks, geosynchronous satellites around the globe. They're critical for providing always-on networking. They let you reach hard-to-reach places that might be rural or remote, but in particular during natural disasters, geosynchronous satellites are still available when land wire lines might be down or wireless might be down. And in particular, the technologies, like lots of networking, has been increasing, and about 20-fold recently, such that we have very reasonable bit rates over geosynchronous satellite networks. The challenge with them, of course, is not necessarily the bit rate, but the latency. Because of the physics involved, it takes about 150 milliseconds to bounce a signal up and then 150 milliseconds down. That's sort of one way. And then, of course, TCP does a round trip time. So we're talking about 600 milliseconds in round trip times. And for congestion control protocols like TCP, the latency impacts the bit rate. And it impacts the bit rate because it impacts the way that the window grows. So remember, from your TCP, basically the window can grow every round trip time it gets an act back. And you have, again, slow start where it can double, but even during congestion avoidance increases. So that round trip time impacts the window growth. The exact growth depends upon the congestion controller algorithm. Most of the internet runs with TCP Cubic, whether that's Windows or Linux or Mac, where Cubic is this loss-based algorithm where the window is going to grow, but then it's going to change size depending on packet losses. There's some emerging congestion control research that has different protocols that have some different behaviors. TCP BBR, published and used by Google, doesn't use loss as a measure to adjust the window size. It uses a bandwidth laid product. So it computes the round trip time, and it computes the available bandwidth, and it sets the window size accordingly. PCC is another approach where it comes up with this function to decide utility, and it'll use that to pick the window size. So it does these little mini experiments to pick the best window size that has the best utility. And that's based on, there's different functions, but based on a measure of loss and round trip time and throughput to decide on what it's going to actually choose for window size. Hybla is actually an older protocol that's based on Reno, but it's basically tuned its window growth to the round trip time. So it looks at the round trip time. If it's high, it'll say, well, I'm going to ramp up quicker so I don't have this sort of slow start with that high round trip time. So it's tuned for satellite networks. So these are some four choices that we're actually going to look at. And in particular, there's been a fair amount of research in satellites, but a lot of it hasn't happened over actual networks, where a lot of the work that's measured TCP performance over satellites has been through simulation or emulation. So we have an opportunity here to actually use a real commercial satellite network. And rather than just sort of a single flow running, again, if you have emerging protocols and you're running multiple flows, how do they interact? And that's what this paper is about, using an existing satellite network and looking at the interaction between, so your Cubic protocol and one of these other protocols up here. Right, so that's where we're going with this research, and that's what this paper is about. And so just briefly, that's my introduction. I'm going to talk about our methodology. So how do we set up these experiments to measure it on our actual satellite network? And then I'll walk through results and then summarize some conclusions. So in order to look at performance for over the satellite network, we set up a client as the last mile connection. So this could be your client in the middle of the Himalayas or somewhere where there's no wireline network, or the disaster strikes and it's your last mile client. So the satellite actually connects that client to the rest of the internet. And then we are going to do downloads from my servers at WPI. So we have some servers at WPI. They're going to do downloads. And so again, we're going to run two flows across it. So one is going to be my Cubic, and it's going to compete with a second flow, both coming from separate servers at WPI. All right, so we sort of have some baseline performance measurements, but then those two competing flows are both going to be doing bulk downloads. Starting simultaneously, they're running using iPerf. So looking at overall performance. And again, mostly what's the throughput like, but we can also measure the round trip time. So what's happening with the queuing, retransmission if there's loss, and then we can look at the congestion window size. Right, so that's our setup. And again, sort of main metrics, again, 2 flows. We do repeated runs. So the flows run for several minutes each, repeated runs over and over again, back to back, so that we keep them temporally consistent. We're going to report 10 runs per condition. And I'll show you those results in a second. And so that's where we're moving to. So again, we're doing a flow competing with another flow where Cubic is the baseline flow. So Cubic is, again, the default for nearly all internet connections today using a Cubic congestion control protocol. And so how does it compete with another Cubic? So let's look at those results. And then how does it compete if the second flow is a BBR flow? Then how does it compete with PCC? How does it compete with Hybla? Then we'll step back and we'll try and provide sort of an overall, how do they compare, with some thoughts on that. Okay, and I'll end with conclusions. All right, so first, how does Cubic compete with itself? So this is, again, 2 flows. One's the default Cubic, and then we run a second Cubic at the same time. We look at performance. So this graph, these graphs depict that, where, again, several minutes, but this is about 2 minutes of a flow. This is time on this axis. It might be hard to see the numbers, but it's about 2 minutes of time. So we're reporting values once per second. And then this top graph is throughput. So this is throughput, where, again, our link has a capacity of about 144 megabits per second. And we're depicting 2 flows, and they're both Cubic in this case. So there's a orange line and a blue line. And this is, again, many runs. So this is the thick line is the mean for those runs. There's a little bit of shading, and those are actually 95% confidence intervals around those means. So you can see there's a slight difference maybe in the blue and the orange here. So again, the throughput graph, the Cubic, the flow that starts a little bit first gets a little bit more, but overall they're pretty fair. They're pretty consistent. They each get about half the bandwidth, which is maybe what we expect. They share it fairly. They each get about half the 144 megabits per second. So that's that top graph. These other ones I'm not going to talk about too much just for space, but you can look at them in the paper. They provide, again, a more complete picture of what's happening on the network in terms of the round trip time at the bottleneck link. And again, here they're shared, and it's about at 700 milliseconds or so, which is my satellite RTT. And then I can look at the congestion windows, again, consistent across both flows. And then for some graphs, this might be a little bit interesting, which is, how much loss do they experience? Because that's how Cubic adapts. Okay, so Cubic versus Cubic, kind of the first test. So you run 2 flows across satellite, share pretty fairly. Takes them a little while to ramp up, about 20-ish seconds, but they kind of get to steady state, they run. So that's my satellite link. So let's look at some of the other protocols. So next we'll take a look at BBR. So this is now, again, 2 flows. One's the default Cubic, the other one's now my BBR flow. And so the BBR is depicted in blue, the Cubic's in orange. And again, this is the same axes, 2 minutes of flow, and this is throughput on the top. And the BBR is blue. And so you can see the BBR is way higher in this case than my Cubic. My Cubic's way down here. So the BBR flow is definitely getting much more bandwidth, on averaging 120-ish, 125 megabits per second compared to the TCP the Cubic at the bottom getting the rest. So it dominates. I mean, this early phase looks about the same maybe, but definitely BBR is getting much more bit rate. You see considerably more loss here. Now, again, you say, what's the difference here? Well, again, Cubic is reacting to that loss. It's a loss-based congestion control protocol. BBR is not. BBR doesn't respond to loss as a congestion signal. And it computes a round trip time measure and a throughput measure and available bandwidth measure, and he uses that to set its congestion window. So that's having a big effect in terms of Cubic responding and BBR not. And so they're very disparate bit rates here. So PCC is next. So again, this is 2 flows. One's now PCC, one's Cubic. So PCC now is this blue one again. And in this case, Cubic is higher. So Cubic is getting more bit rate than PCC, right? So Cubic's about at 100-ish or so, and PCC is around 40. So it's kind of flipped from the BBR case. And again, PCC has this utility function where it does these mini experiments, and it changes the bit rate, and it tries to use a utility to decide if it should increase or decrease its throughput. And utility function in this case is based on latency, loss, and throughput. So it has this utility. And what the utility function here isn't providing sort of fair throughput, meaning Cubic's doing better, and PCC decides that this is sort of maybe the best utility down here, which is a fair amount lower. Now, there's not a lot of loss in the system, a little bits and pieces here, but mostly not. Right, so PCC is basically deferring to Cubic in this case. Our last snapshot here, last of the four, is Hybla. Again, Hybla is sort of tuned to high latency. And what it does is it changes how fast it ramps up. So how fast it grows the window in relation to sort of this base RTT. So it says, oh, if your RTT is higher than a typical wire network of 25 milliseconds, let's grow the window faster. And so here's Hybla with this blue at the top. And again, that's what we see is it ramps up much quicker, right? Versus my Cubic, which again takes a while to ramp up. And so Hybla is doing a lot better in this phase. So it's actually, getting up to that available bandwidth. It's much higher. Overall, it ends up kind of sharing fairly over here, but that takes a while. So this first startup phase, Hybla is much better. Again, the cost maybe is that this RTT, it has it has potential to overshoot that initial SS thresh and that threshold when it causes loss. And that's maybe this first phase, but it gets sort of higher bit rate there. Okay, so if we take those four and we step back a bit and we say, I'm sorry. One other condition we've noticed with Cubic is that Linux Cubic has this algorithm called high start, which tries to anticipate what I just said, which is overshooting that initial slow start, and it exits high start early. Sorry, it exits slow start early. So it's a parameter, and we've noticed that what's happening here during your normal Cubic is it exits early, so we can turn high start off. Normal Cubic with slow start, but it doesn't ever exit until it hits that SS thresh, right? So that's this blue line is what happens when we turn high start off, and sure enough, it actually ramps up much quicker because it doesn't exit slow start early, unlike the sort of the default. So this was if you take your server, your Linux server over the satellite and you tune it by turning high start off, you can get this behavior, which is overall fairness here once you start up, but again, a better startup performance. Now we step back, we take a look at the four algorithms and maybe this hard start one too, and we compare them to each other. We can kind of summarize here where this is a heat map showing the throughput differences. So again, this is my Cubic versus Cubic. And then so the heat map says if the default Cubic flow is doing more, it'll be kind of this orangish, really bright. If the competing flow is doing more, it'll be this heat map, this blue, this kind of bright blue. Right, so Cubic versus Cubic again then is fair. It's black, right in the middle. I mean, it's not much of a throughput difference, 7 megabits per second. But that's only a little startup. It's about the same. And then these other algorithms, you can see, well, this is in contrast to BBR. BBR bright blue. So BBR overall does dominate sort of Cubic. It does a lot more. It's high, on average. It's sorry, that number is a 91 megabits per second more. So it's way more, right? It's really in this region right here. In contrast, PCC, in this orange, it gets dominated by Cubic overall. Hybla does a little bit better because that startup phase is better. It's sort of here. And then Cubic with high start, again, that startup was better, but it's here. And in fact, I'm sort of teasing out that startup versus steady state. And that's what we can do. We can kind of look at those phases. So this is the more complete picture. Where if we take a look at that first 15 seconds, that's the startup phase. And then I can look at the last half. So after you've gotten past the startup phase, you're in the steady state phase. And then I just told you about the overall, but the steady state, you sort of have this flip where again, Cubic is fair to itself at all phases. BBR, again, is fair at startup. Likewise, PCC is also. They're fair to Cubic at startup. It's when you sort of get to steady state that, again, BBR really dominates and PCC defers. Right. And in contrast, Hybla, of course, starts up really, really fast. And then it ends up being, fair later. And likewise, if you turn off the high start, sort of the same. So this is sort of a more complete picture of what's happening. All right, so let me summarize where we are. Cubic versus Cubic is fair to itself, kind of at all phases. BBR is fair at startup, but overall it dominates. Whereas PCC is also fair at startup, but it gets dominated. And then Hybla, dominates at startup, and then it's kind of fair during steady state. And so these are, again, for a satellite network. We anticipate these holding for other high BDP, high bandwidth rate product networks, in particular when there's a large queue size. Right, so there's some future work we're looking at. There's different kinds of tuning possibilities for the startup phase that are of interest. So the initial congestion window, there's some sort of state you can preserve in BBR, and there's some work in PCC that might do that. Another alternative that's interesting to TCP is a protocol called QUIC that you might have heard of. And QUIC replaces TCP, has some apparent advantages for web-based traffic, and has a pluggable congestion control in it also. So how does QUIC work? And then you, in many cases for a high bandwidth product network, you put boxes in the middle boxes that do performance enhancement. So performance enhancing proxies. So how do those work? Now, in particular, these are interesting. They work with some protocols, not others. In particular, they can't work with protocols that are encrypted, but we'd like to look at that sort of as a full rich space of performance. Thanks for tuning in. Appreciate your attention, and hopefully I'll have a chance to talk and answer questions.